Now, we are practicing the problems based on stoichiometric calculations. So, here we have one problem, that is, find the volume of CO2 liberated at STP when 24 grams of carbon is completely burned in presence of oxygen. There is a slight difference between the present problem and the problems which I had done in the previous class. So, both are based on the same principle, but there they ask us to calculate the amount of carbon dioxide that was liberated or amount of sulfur dioxide that was liberated. But here they are asking to calculate the volume of CO2 gas liberated at STP conditions. In STP conditions, we know that 1 mole of any gas will occupy 22.4 liters. That will be the standard value, it will not change. At STP conditions, 1 mole of any gas, if a matter is in a gaseous state at STP conditions, it occupies 22.4 liters at STP. Now, in the present problem, carbon was burned in presence of oxygen to give carbon dioxide. So, the first step we have to do, what we have to do is, first write a chemical equation for the above said problem. So, carbon was burned in presence of oxygen to give CO2. So, 1 carbon reactant side, 1 carbon in product side, 2 oxygens in reactant side, 2 oxygens in product side. So, the equation was balanced. Now, in the second step, if you substitute the atomic weights, 12 units of carbon is reacting with 32 units of oxygen to give 44 units of carbon dioxide. So, here if 12 grams of carbon is taken, it reacts with 32 grams of oxygen and produces 44 grams of CO2. Since 44 is the molecular weight, 44 grams will be equal to 1 mole. So, if it is all in grams, 12 grams, 32 grams and 44 grams. This is equal to 1 mole. This is equal to 1 mole. So, 1 mole of a gas will occupy 22.4 liters at STP. 22.4 liters at STP. That is the volume of CO2. Now, this volume of CO2 is liberated from 12 grams of carbon. So, 12 grams of carbon produces 22.4 liters of CO2 at STP. Now, they are asking the amount of CO2 that was liberated when 24 grams of carbon was completely burned. So, from 12 grams of carbon, 22.4 liters of CO2 is liberating. Then 24 grams of carbon produces or liberated how many liters of CO2? So, it will be 24 by 12 into 22.4. So, it will be 2 times. So, it will be 44.8 liters. This is the volume of CO2 at STP that was liberated when 24 grams of carbon was completely burned. So, here in the previous problems, mass was asked. So, we have compared this mass of carbon with mass of carbon dioxide. Now, in the present problem, they are comparing the mass of carbon with volume of CO2 liberated. That's why here, instead of 44, we have taken 22.4. That is the basic difference between previous problems and this problem. They ask us the amount. That's why we taken 44. Here they are asking the volume. That's why we are taking 22.4. So from 12 grams of carbon, 22.4 liters of CO2 at STP is liberated. Then 24 grams, how much? 24 by 12 into 22.4. So it will be 44.8 liters of CO2 at STP. Now calculate the volume of CO2 gas at STP liberated when 25 grams of calcium carbonate is completely decomposed. Calculate the volume of CO2 gas at STP liberated when 25 grams of calcium carbonate is completely decomposed. So we have already know that when calcium carbonate is decomposed, it decomposes to give calcium oxide and carbon dioxide. So CaCO3, when decomposed, it gives us calcium oxide and carbon dioxide. Now, the molecular weight of calcium carbonate. Here, calcium atomic weight is 40. Carbon atomic weight is 12. Here 3 oxygens are there. So the total of 3 oxygens, 3 into 16, it is 48. So when you add all the 3, you will get 100. So this is the 100 is the molecular weight of CaCO3. So calcium carbonate molecular weight is 100. Calcium carbonate molecular weight is 100. Similarly, calcium oxide, calcium is 40, oxygen is 16. Oxygen is 16. So calcium oxide molecular weight is 56. So the molecular weight of calcium oxide is 56. Here in CO2, carbon is 12 plus 2 oxygens, 2 16s, 32. 12 plus 32, it is 44. Now 44 plus 56 will be equal to 100. It should be always equal. Now what is the relation they are asking? When this shows that 100 grams of calcium carbonate decomposes to give 56 grams of calcium oxide and 44 grams of carbon dioxide. This 44 is the molecular weight of carbon dioxide. If we express the whole thing in grams, 100 grams of CaCO3 decomposes to give 56 grams of CaO and 44 grams of CO2. But in this problem they are asking the volume of CO2 gas at STP. 44 is the molecular weight of CO2. 44 grams is the gram molecular weight of CO2 or 1 mole of CO2. So 1 mole of CO2 at STP conditions, it will occupy 22.4 liters volume. Now this 44 grams of CO2 at STP occupies 22.4 liters. Now the thing, how to compare this? 100 grams of CaCO3 give 44 grams of CO2 or 22.4 liters of CO2 at STP. So they are asking the same thing. What volume of CO2 is liberated in the complete decomposition of 25 grams of CaCO3? Now here we have the relation, that is 100 grams of CaCO3 liberates 22.4 liters of CO2. 100 grams of CaCO3 liberates 22.4 liters of CO2. Because according to this equation, 100 is the molecular weight of calcium carbonate, 56 is the molecular weight of CaO, and 44 is the molecular weight of CO2. So, when in the decomposition of calcium carbonate, the mass ratios are 100 grams of calcium carbonate decomposes to give 56 grams of calcium oxide and 44 grams of CO2. The same 44 grams of CO2 will occupy 22.4 liters at STP. So, in other words, we can say that 100 grams of CaCO3 on decomposition, it can give 22.4 liters of CO2. So, 100 grams of CaCO3 can give 22.4 liters of CO2 at STP conditions. Now they are asking the amount of CO2 that liberated in 25 grams. So 25 grams of CaCO3 can give how many liters? So 25 by 100 into 22.4, 25 4 times, 4 here, 5.6 times. So from 25 grams of CaCO3 on complete decomposition, you are going to get 5.6 liters of CO2. 5.6 liters of CO2. That is the volume of CO2 that liberated in the complete decomposition of 25 grams of CaCO3. Once again, here the problem is calculate the volume of CO2 gas at STP liberated when 25 grams of calcium carbonate is completely decomposed. The equation for the decomposition of CaCO3 is CaCO3 gives CaO plus CO2. CaCO3 gives CaO plus CO2. Now, if you substitute the molecular weight of all the compounds, 100 is the molecular weight of CaCO3, 56 is the molecular weight of CaO, and 44 is the molecular weight of carbon dioxide. That means the mass ratios of calcium decomposition of calcium carbonate is as follows. That is 100 grams of calcium carbonate on decomposition gives 56 grams of CaO and 44 grams of CO2. This 44 grams of CO2 is said to be 1 mole because 44 is the molecular weight. So 44 grams will be the gram molecular weight or gram mole or simply as mole. So 1 mole of any gas at STP conditions, it will occupy 22.4 liters, that we call it as a gram molar volume. So the carbon dioxide volume in the decomposition of 100 grams of CaCO3 is 22.4 liters. So now they are asking the volume when 25 grams was decomposed. So if 100 grams of CaCO3 is decomposed, it produces 22.4 liters. For 25 grams, how many liters? 25 by 100 into 22.4, that is 5.6 liters. So 5.6 liters of CO2 gas is liberated in the complete decomposition of 25 grams of CaCO3. Here is another problem. Calculate the amount of KClO3 required to prepare 6.72 liters of O2 gas at STP conditions. We have already done this problem, of course in a different manner. The oxygen is prepared by the decomposition of potassium chlorate. We know that the decomposition of potassium chlorate is as follows. KClO3 gives KCl plus O2. This was the skeleton equation for the preparation of oxygen by the decomposition of KClO3. Now, if you first, this is the equation. Now you have to verify whether it is balanced or not. 1 potassium in the reactant side, 1 potassium in the product side, 1 chlorine in the reactant side, 1 chlorine in the product side. So potassium and chlorine both are balanced. But in the case of oxygen, there are 3 oxygen atoms in the reactant side, but only 2 oxygens are there in the product side. So to balance this, you have to multiply KClO3 with 2 and this oxygen the 3. So that you will have 2 3s are 6 oxygens and 3 2s are 6 oxygens. Oxygens were balanced, but at the same time KCl was imbalanced. 2 KCl. So here if you put 2 here, you will get 2 KCl. Now if you apply the molecular weights, here the molecular weight, if you calculate for KClO3, we have already, in the previous problem, we have already calculated. For K, atomic weight is 39. For Cl, atomic weight is 35.5. So 3 oxygens are there. So 3 into oxygen atomic weight is 16 into 3. So it will be 48. So the total will be 122.5. This is the molecular weight of KClO3. So 122.5. Now they are asking the amount of oxygen or the volume of oxygen from KClO3. Now here 3 into 32, that is 96 is the molecular weight, total mass of oxygen. So if you want to know the volume, this 32 grams of oxygen will occupy 22.4 liters. So the volume of oxygen that liberated is 3 into 22.4 liters. 3 into 22.4 liters. So it will be 67.2 liters. 67.2 liters. That is, what they are asking? Volume of O2 gas is 6.72 liters with mass of KClO3. Now here according to this equation, 2 into 122.5, that is 245 grams of KClO3 can produce the 67.2 liters of oxygen. That means 67.2 liters of O2 at STP can be prepared from 245 grams of KClO3. 245 grams of KClO3. 67.2 liters of O2 at STP can be prepared from 245 grams of KClO3. Now here you should prepare 6.72 liters. Then 6.72 liters of O2 at STP conditions can be prepared from how many grams? So 6.72 by 67.2 into 245. So it goes here 10 times, then it will be 24.5 grams. So 24.5 grams of calcium chloride, potassium chlorate is required to prepare 6.72 liters of oxygen gas at STP. So once again, calculate the amount of KClO3 required to prepare 6.72 liters of O2 at STP conditions. First you should know how O2 is prepared from KClO3. You should know that process because this is a very important and familiar reaction. KClO3, potassium chlorate. When potassium chlorate is heated, it decomposes to give potassium chloride and oxygen. Potassium chlorate on heating decomposes to give potassium chloride and oxygen. KClO3 gives KCl plus O2. KClO3 gives KCl plus O2. That is the required equation for the above reaction. Now, in this reaction, whether it is balanced or unbalanced, you have to verify. If you observe this reaction, one potassium is there before balancing, one potassium in the product side and reactant side also. One Cl is in the reactant side and only one Cl is in the product side, but only 3 oxygens are there in the reactant side, but only 2 oxygens are in the product side. To balance that, a coefficient 2 is kept before KClO3 and coefficient 3 should be kept before oxygen. That means 2 KClO3 gives 3 O2. Now KCl's are unbalanced, so you have to add 2 KCl. Now from this equation, 122.5 is the molecular weight of KClO3. So 2 moles of KClO3. So 2 into 122.5, that is 245 units of KClO3 is producing 3 into 32. 32 grams means here at STP conditions it occupies 22.4 liters. That means 3 into 22.4 liters of O2 gas at STP. That means if you decompose 245 grams of KClO3, there you will get 22.4 liters of O2. From 245 grams you are getting 3 into 22.4, that is 67.2 liters of O2 gas. So that's why 67.2 liters of O2 gas can be prepared or liberated when 245 grams of KClO3 is decomposed. But here our requirement is only 6.72 liters. So 6.72 liters of O2 gas is liberated from what the weight of KClO3. So 6.72 by 67.2 into 245. So it will be 24.5 grams. This is the amount of KClO3 required to prepare that above said oxygen. We have another problem. Calculate the volume of O2 at STP required for complete combustion of or completely burn 12 grams of magnesium. We know the equation or the required for the above reaction. Magnesium burn in presence of oxygen to give magnesium oxide. Magnesium burn in presence of oxygen to give magnesium oxide. Now, here one magnesium, product side is also one magnesium, but 2 oxygens are there only 1 oxygen, so you have to write 2 here. To balance it, you have to put 2 here. 2 Mg plus O2 gives 2 MgO. This is the required equation, balanced equation. Required balanced equation. Now, according to this equation, 2 into 24 is the atomic weight of magnesium. 2 into 24 grams of magnesium is reacting with 32 grams of oxygen to produce magnesium oxide. So here they are asking the volume of oxygen at STP. So this 32 grams of oxygen will occupy 22.4 liters at STP. 22.4 liters at STP. That means this 48 grams of Mg requires 22.4 liters of O2 at STP. That is the ratio. 48 grams of Mg requires 22.4 liters of O2 at STP. Now what they are asking? The volume of O2 required for the burning combustion of 12 grams of Mg. Here for 48 grams of Mg, you require 22.4 liters. Then for 12 grams of Mg, requires how many liters of O2? So 12 by 48 into 22.4, 4 times, so 5. So 5.6 liters of O2 gas is required for complete combustion of 12 grams of Mg. Just simple. In any the stoichiometric problems, first you should observe what is the equation or the reaction. What is the reaction involved to solve the given problem? So generally they won't go for a new and unknown equations. Here they will give you a well-known reactions which are very familiar to you and which are within your syllabus, which are frequently discussed in the classrooms. They won't give you a new reaction, because if new reaction was given, even we are also unable to do it. So they won't give you, but they may give the equation or the reaction from any chapter in your syllabus. It may not belong to the particular topic which we are dealing. In some other topic, that reaction may present. So you should remember each and every reaction which was present in your syllabus. If you know those reactions, and if you are able to write the equation for the above said reactions, and if you are able to calculate the molecular weights of the compounds that were involved, then it is very easy to solve this type of problems. So if you go on practicing it, you will be adjusted and you will able to do any type of a chemical reaction. So we have another problem, that is calculate the volume of SO2 gas formed at STP in the complete combustion of 8 grams of sulfur. The volume of SO2 gas at STP that was formed in the complete combustion of 8 grams of sulfur. We know that sulfur, when burned in presence of oxygen, it will give us sulfur dioxide. For that, the equation is S plus O2 gives SO2. It's very familiar and common reaction. S plus O2 gives SO2. Now, if you apply the stoichiometric proportions here, one sulfur in the reactant side and one sulfur in the product side, 2 oxygens in the reactant side, 2 oxygens in the product side. So, it was a balanced equation. Now, you can apply the stoichiometric proportions. So, here if you apply it, 32 units of sulfur reacts with 32 units of oxygen to give 64 units. That means 32 grams of sulfur will burn in presence of 32 grams of oxygen to give 64 grams of sulfur dioxide. This 32 grams of oxygen will occupy 22.4 liters at STP, and the 64 grams of sulfur dioxide will also occupies 22.4 liters at STP. Now what they are asking, volume of SO2 gas formed when 8 grams of sulfur was completely burned. So they are asking the relation between sulfur and volume of CO2. Sulfur to the volume of CO2. So from this equation, it is evident that 32 grams of sulfur can form 22.4 liters of SO2 gas at STP. 32 grams of sulfur can form 22.4 liters of SO2. 22.4 liters of SO2 at STP. Remember, it is only at STP conditions only, this volume, not in other conditions. So 32 grams of sulfur can form 22.4 liters of SO2 gas at STP. Now here we have only 8 grams. So 8 grams of sulfur can form how many liters of SO2 at STP? That's the question. So it will be 8 by 32 into 22.4. So here it goes 4 times, 5.6. So we will get 5.6 liters of SO2 gas in the complete combustion of 8 grams of sulfur.